Great. So this is a little bit unusual for me presenting virtually, and I'm happy to take questions at the end, but also feel free to follow up with me afterwards. My email will be on the last slide. If there's anything that's a kind of longer format discussion, I'm happy to answer those questions offline as well. So this is joint work with my advisor and an undergraduate research assistant. I'm a PhD candidate at Brown University in the computer science department. And we're tackling a really interesting problem, I think, which is, can we predict student responses to assessment items? And the context for this is we've given a student, say, part of an exam. They've answered some of the questions. And now the question that we're trying to answer is, can we predict their, say, correctness on the remaining items? And you might be asking, why do we do this? We could just give them the exam. But there are a couple of applications outside of just maybe speeding up an exam to guessing answers. So the first thing is that if we are able to predict a student's response to a question, say whether they get it correct or incorrect, without asking them the question, but conditioned on their answers to previous questions, this can give us insight into the curriculum that the course should have. So that's this left icon. If we have a set of questions where not having answered them correctly leads to the conclusion that they won't answer a later question correctly, then that says that in some sense those are probably prerequisites of this harder question that they're unlikely to get correct. The second thing is that we can do efficient tracking of student progress. If we have a curriculum, we can give them fine-grained feedback on what they've learned and haven't learned, and can give them a more precise measure of how they're progressing than just their average grade over the course so far. And the final thing, and this is the thing that I'm especially excited about, is that we could use this to do adaptive testing. If you think about it, most exams are pretty inefficient because there are going to be, for any given student, a number of questions that are just too easy, so they're not really testing the frontier of their knowledge. And then there's probably going to be a set of questions that are too hard. There's something they don't understand or they haven't quite figured out yet. And those questions they'll be likely to get wrong, and it'll just be a kind of futile struggle. If we could cut out those portions of the exam, we could administer assessments more frequently and more efficiently without increasing the amount of, say, class time taken up by administering those assessments. So there are two main approaches to predicting what a student knows or what they'll be able to answer correctly based on their history. And the two approaches are both kind of probabilistic, Bayesian type machine learning algorithms, but they're pretty different. On the left-hand side, we have item response theory. And the assumption behind item response theory is that there's a small number of parameters. And if we know those parameters, then predicting the likelihood that someone will get something correct is independent of their performance on all of the other assessment items. So the problem of item response theory is, let's figure out these parameters so that we can predict responses accurately. And these strong independence assumptions make it easy to apply, and the number of parameters is very small, so it's easy to fit. On the other side, we have a discrete graphical structure where we build an explicit prerequisite map, and we try and use that to predict responses to future questions. And this is more involved. The model optimization is more complicated, but it potentially gives us more fine-grained information. For item response theory, I'll go over these parameters quickly. C represents the probability of guessing an answer. D represents a difficulty threshold for the question. Theta is the student's ability. So we have a sigmoid curve where your likelihood of getting it correctly diminishes as your ability level is less and less than the difficulty measure. And A is a discriminability coefficient. So some questions are just more precise than others in terms of delineating student ability relative to their difficulty. So in contrast, the Bayesian prerequisite modeling is using a lot of specific features like, did you get this other question correct? So there's an explicit interdependence between the assessment items. So item response theory benefits from these strong independence assumptions because it's easy to optimize the parameters. The model inference is fairly fast, and this is commonly used in practice for adaptive testing. One limitation is that it's really difficult to capture multiple dimensions of knowledge or multiple dimensions of difficulty. So if you have anything that's, say, cross-disciplinary or draws on multiple areas of expertise, it requires a lot of expert intervention in order to design a model that actually represents that well. And then in contrast, Bayesian prerequisite modeling has much weaker independence assumptions, but is generally more accurate in terms of predictions. The downside is that the models quickly become computationally intractable. And the only ways that we know of so far to reduce that complexity involve injecting expert input, for example, by collapsing multiple assessment items down to an individual node in this prerequisite graph. So the goal of this talk is to somehow combine these approaches, to have weaker independence assumptions than item response theory, but greater accuracy, weaker assumptions than item response theory, but greater accuracy than item response theory, and still get this in a reasonable amount of time. And as an added bonus, we're going to try and remove the expert input to these processes so that we have something that's truly empirical and scales more effectively than having an expert sit down and validate a curriculum model, for example. Okay, so the question is, how do we evaluate and compare these two different approaches that are generally used for different problems on a kind of standard benchmark or standard framework using only student data? So again, we're trying to get rid of the expert insight to come up with something that scales beyond what we have experts available for. So let's look at the applications that we've brought up. Maybe one of them can be a good performance metric. We could try and validate whether or not a curriculum is correctly inferred, but we don't have a ground truth on what the curriculum should be. So that's going to require expert input. And for similar reasons, tracking student progression is probably going to require expert input in order to validate the models that we're testing. So that leaves us with adaptive testing. What we're going to do is design a framework for testing algorithms that answer this question of how likely is a student to get this question correct using an adaptive testing framework. And the only challenge we have to overcome is that in adaptive testing, that is choosing which questions to ask based on previous responses, we have this trade-off between efficiency, limiting the number of questions that we ask, and accuracy, getting a lot of information about what the student knows. In order to navigate that trade-off, we're going to introduce a parameter gamma. And the intuition behind gamma is that this is a level of confidence at which an adaptive testing algorithm should be willing to ask the question. So if gamma is 0.75, then if I'm less than 75% confident that a student will answer something a particular way, then I should ask the question. Otherwise, I can feel free to guess it. And we have a scoring mechanism that prioritizes that kind of policy. Okay, so the general framework is that we have this algorithm. It has a set of questions that it can ask. At some point, it's going to stop asking questions and just guess what the student will respond to all of the rest of them. And there are two baseline algorithms we want to test in this gamma evaluation framework. So the first one is one where we guess that a student will respond a particular way, and we have some confidence alpha that they will respond the way that we think they will. And with this gamma scoring rule, we've worked it out exactly so that when I have confidence alpha, I get exactly score 0 in expectation. We also have worked it out where the y-intercept is the fraction of questions that are likely guessed correctly without having to be asked. And so we'll get approximately alpha of those correct. And in the middle, there's this sort of smooth curve. Once we get beyond confidence alpha, we have increasing negative penalties for incorrect guessing. And at that point, we're strongly incentivized to just ask all of the questions that we don't have sufficient confidence for. So what this means is that for these two baselines, we're going to have some range where we could just guess, say, the majority answer on a set of questions. But at some point, our accuracy is going to be small enough that we should just ask all of the questions, and we'll flatline after that on these curves. So we'll have some experimental plots that look a little bit like this in the future, and that's where this baseline comes from. The final point is that as gamma approaches 1, the negative penalty for incorrectly guessing a student response goes to infinity. And so getting any value that's larger than 0 in terms of performance on this type of test is highly impressive. If we have some noise in our responses, we'll call it epsilon. This could be a guess probability or something like that. The sort of maximum interesting range is going to be up to 1 minus epsilon, because we wouldn't expect any algorithm to be able to correctly predict student responses with accuracy higher than that. Okay, so this is our evaluation framework. And now we've developed an algorithm that combines some of the best aspects of item response theory and Bayesian prerequisite inference. We call this directed item dependence and confidence thresholds, which has the nice acronym of DIDACT. And the idea is that we're going to quickly build up this directed graphical structure that represents the prerequisite relations based on pairwise tests, statistical tests. After we've done those statistical tests, we'll develop an inference procedure which assumes a lot of independence from things that aren't directly related in the graphical structure. In particular, we will assume that all the items are independent, conditioned on any intermediate nodes in the in a path between two groups. So we have this DAG over equivalent sets of questions. So here B and C are evaluated to be equivalent. The rest of them are by themselves, and we have some directed relationships. And the idea behind DIDACT is that B and C are independent of, say, of F and of D. They're independent of G conditioned on E. So if we know any of the nodes in between on this directed path, then we only have to worry about the nodes that are closest on that path. So what does this inference look like? If we know that they answered E correctly, we have some strong information that says that all of the prerequisites they probably will also get correct. And we maybe have a weak amount of information in terms of their likelihood of getting G correct, but that's really only a small amount of data. If we also know that they got either B or C correct, now we no longer care about the answer to E in inferring the response to A. On the flip side, if they get question E incorrect, that gives us a strong amount of information about their likelihood of getting the harder question G correct. So we have this sort of one-way propagation of information depending on whether the answer is correct or incorrect. We have some weak information about some of the things that come before, but we can't really base a lot on that. And again, if we know the correctness value for either B or C, then we no longer care about E when making inference about A. Okay, so if we were to try and predict the response to A based on this set of responses, the only one that we care about is E. And this is just to highlight that by using this graphical structure, we can greatly reduce the complexity of doing inference and predictions over all of the variables that we haven't observed yet. So this is very similar to a Bayesian network in the sense that we're using a graphical structure, but it exploits many of the independence assumptions that make item response theory efficient. In particular, we assume that all of the influences are direct, so we don't have to propagate information through the network. And we also assume that they're independent. So rather than building these exponentially large conditional probability tables, we just have independent pairwise influences on the items that we're trying to predict. Okay, so what we've done is we've developed an algorithm which is an alternative to these accurate but expensive Bayesian procedures. On the left-hand side, you can see a runtime of an approximate Bayesian model versus DIDACT. DIDACT is much faster and doesn't blow up exponentially as we start trying to do inference over a large number of questions. On the right-hand side, you can see that DIDACT is comparable in accuracy. For runtime purposes, we were only able to run this experiment with 5 real-world questions, which isn't a lot, but again, the Bayesian network inference becomes prohibitive beyond that. The Bayesian network is able to answer 3 to 4 questions on average based on the asking the other ones, whereas DIDACT is only able to do 2 to 3, but that's still pretty impressive. That's like skipping out on half of this assessment just based on accurate predictions to these other questions. Okay, so here's the comparison that we care about, which is how does it perform relative to item response theory? And we use 2 real-world data sets in this adaptive testing evaluation framework. And the one on the left deals with a set of 20 questions involving subtraction of fractions in an elementary school classroom. The data set on the right involves answering a set of SAT questions. So on the data set on the left, we see that there's a clear performance difference between DIDACT and item response theory. Because we're explicitly utilizing these prerequisite relationships, we're able to make much more accurate predictions about what a student will get correct or incorrect, and this leads to being able to ask fewer questions overall, or guessing more questions accurately. What you will notice is that both of them are overconfident about their accuracy towards the right end of the plot. So both of them are highly confident in some answers that they then get wrong, and this leads to these large negative penalties. On the right-hand side, the difference is a lot less clear. It's even possible that IRT is outperforming DIDACT, although the confidence bars don't give us enough information to conclude that in a statistically significant way. But there's a question here. Why is it that on the data set on the left, we have this huge performance difference, and on the data set on the right, we don't? So the hypothesis that we came up with is that fraction subtraction is a fairly narrow topic, and the likelihood of having explicit dependence relationships between questions on that assessment is pretty high. If I have some prerequisite skill, like being able to find a common denominator, and I'm not able to apply that on a simpler question, being able to apply that on a more complicated question, it's almost certain that I'll get it wrong. And so on the left-hand side, we have these strong dependence relationships which break the assumption of item response theory that all of the questions are independent, conditioned on difficulty. On the right-hand side, we have a bunch of SAT questions which come from a variety of topics, and within those topics are probably addressing different subtopics. And so there's a strong likelihood that the questions are effectively independent, and that's why the item response theory does comparably to DIDACT. So in order to test this hypothesis, we generated some synthetic data. In the data set on the left, there is a chain DAG of questions where you can only get one correct if you understand all the prerequisites, and they're in a chain. So there's an exact point where all of the questions to the left you know, and all the questions to the right you don't know. Because this is sort of an extreme example of having strong dependency relationships, we expect DIDACT to outperform item response theory, and in fact that's what we see. The performance at the right-hand side, there's no stochasticity in this experiment, and so that's why DIDACT is able to maintain this really high performance, even for very high gamma thresholds. On the right-hand side, what we did is we generated a directed acyclic graph of assessment items, but this graph was very broad. So there are a small number of prerequisite relationships relative to the number of total items. And the likelihood of having a random pair of items be directly dependent on each other is very low. And in that case, we see that the performance of the two algorithms is quite comparable. So to summarize, what we've done is we've combined these two different approaches, item response theory and Bayesian prerequisite inference, which are traditionally used for different tasks. Item response theory has been applied to adaptive testing, and Bayesian prerequisite inference has been mostly used for generating curricula. But we've created a framework where the approaches can be directly compared in the context of adaptive testing. And we've built something that exploits the graphical structure similar to Bayesian prerequisite inference, but also takes advantage of strong independence assumptions like item response theory. This algorithm can be used effectively to infer curricula directly from its graphical structure, to track student progress, and also to do adaptive testing. And it meets our goals of being fast, accurate, and not requiring expert input to create or to evaluate. A final point on this is that this is part of a broader project that I've been working on called Quizius. And the goal of Quizius is to take crowdsourced questions and automatically figure out which ones are useful and to do adaptive testing using those crowdsourced questions. So there's some other work I've done in this area. I'm generally interested in assessment. And if you have any questions that we don't get to today, feel free to reach out to me over email. Great. Yeah, I think I breezed through that. I'm sorry I went a little fast. I'm a little nervous about presenting over webcam, but I'll take questions now.